Morning. I want to thank the organizers for inviting me, and when I saw the guest list of who was speaking, I'm deeply honored. I was struck by two things. First, at my age, I'm very interested in cancer, cholesterol, and heart machines. And second, I'm going to talk about pellets. And I had a privilege of accepting an award for our business unit. We received from the Product Development Management Association on how we do innovation. And I'm in a jacket and a tie and bag of pellets. And the co-winners came roaring in on their Harley-Davidson motorcycles, complete with leather, jeans, and chains. The co-winner was Harley-Davidson. And I guess what I'll say is what I said then: without my little bag of pellets, you can't make that machine. So I want to talk about a very simple product that is all over, and the amount of innovation that can go into it, all let out of Texas. We're going to talk about ethylene. You can't get too much simpler, except if you're working on carbon, I guess. And we basically took ethylene with 1 octene and 1 hexene and totally changed the rules using good chemistry. To start out, polyethylene in 1991 started to evolve again, and I was fortunate enough to be there from 1991 until about 2007. And it was actually developed for radar by ICI many years ago in World War II. And the traditional technology, there was a huge range of processes, whether it was gas phase or solution or high pressure. It made a variety of products that were extremely complex. They were basically polymer mixtures. The processes didn't scale well. And literally the phase of the moon, which is basically the temperature, would change the product. We had a tremendous amount of potential because these are very low-cost polymers, but we really couldn't control the structure to realize the potential. So we were searching for new chemistry to let us change the whole game. And actually this change was driven from Texas. And there was 2 outfits, one in Baytown in Houston, that's called Exxon Chemical. And I know Exxon Chemical really well. As a Dow leader, I was partners with them. I was a supplier, I was a customer, and I was a fierce competitor, all wrapped up into one. And Freeport, Texas, and Houston, Texas was Dow, and then of course we had Midland, and I have to keep saying here, it's not Midland, Texas, it's Midland, Michigan, for the Dow Chemical Company, and these 2 companies really drove this technology. There were a lot of other players involved, but if you look real carefully, they're either lined up in one camp or the other, and if they aren't, then they can go to court. I will say there were a lot of lawyers involved. I have one of the most extensive legal educations you can imagine, and thank God that got done in about 1999. And the other thing is the change in chemistry then changed. We changed the process, we changed the materials, we changed the markets, and how we go to market. So we changed a lot of things. And at this time, I'd like to acknowledge John Verity of Exxon Chemical and Charlie Kresge of Dow Chemical, who disavowed all knowledge of this, but did look at my slides and say, yeah, this all made sense. And then Don Paul for looking at it and said, yeah, this is more or less acceptable given you do a good job of presenting it. So it's now 20 years later. It's hard to believe it's 20 years, but the total polyethylene market, to kind of give you size, about $95 billion in 2010, about 145 billion pounds. And sometimes in that business you make 30% and sometimes you make 0. So if you do the advanced math, you can see this is very lucrative or not. Global sales estimate for the new materials is about 13 billion pounds. So from 0, we've built it up to about, 8% or so. Growth rate's a little higher for the new materials than the traditional materials, but the margin is tremendously more. We have a premium of 3 to 60 cents, and nobody would give me any numbers from either side anymore, but I happen to know it's not 3 cents on the average. It's quite a bit more. And the producers get to leverage their new stuff to get business with the old stuff. One of the tricks in the polyethylene game is keep your plants always running. The neat thing is the technology is globally implemented, but the technology center is still in Texas. So let's do a little chemistry. This is a traditional catalyst, very simple. You have basically a mag chloride support. You have titanium on the surface. And that titanium, depending on where it's at the surface and what oxidation state, you have a variety of kinetic sites. Each kinetic site makes something slightly different. And that's why you ended up with a very complex mixture. Each catalyst batch is different. You then activate it, and this diversity really ends up giving you a polymer blend that if you put the catalyst in a given process and the phase of the moon's about right, you make a certain product. Metallocene chemistry, invented by Breslow, but really made successful by Kaminsky's activation. If you look at these materials, these are single sites. All the sites are the same, so you begin to have the ability to control things much better. In this chemistry, typically Exxon favors. Dow tends to favor this chemistry. We called it a constraint geometry catalyst, and it's only got one monocyclopentadienyl group, but it's got a slightly more open catalyst site, which is shown in the blue. And what it allows you to do is reincorporate chains and get you long chain branching. And in a minute, I'll talk what that means. And now, this is the latest version from Dow. If you haven't noticed, these catalysts are getting more and more complex. They're starting to look like pharmaceuticals. And in fact, we use combinatorial chemistry to develop this one. The cost goes up, but fortunately, the activity goes up dramatically. And we're talking 100 times more activity with a cost of about the same thing. But what you do, every time the chemists come up with an improved catalyst, you get improved control. In the polymer structures I talked about, in the conventional LLDP, you can see on the left-hand side, you got different lengths of chains, you got different incorporation rates, and those little marks are signifying when you incorporate an alkene. And you either have a butyl group hanging off or a hexyl group, depending whether it's hexene or octene. And those little branches, or short chain branches, tremendously impact the properties of what kind of polymer you're using. But you can see you have a mixture, and literally the way you would specify it if you were a customer, I want this particular catalyst and this particular product from this particular train, and that's the one I want. And the reason is that each one of those things made a slightly different product, and you wanted to have a consistent product as you can. When the first homogeneous catalyst came out, and these two came out virtually the same time, which allows you to have full employment for lawyers, trust me, and you ended up with Exxon's basically patent area is with their Metallocene. And if you notice, the chain lengths are now about the same length. The distribution of the short chain branching is much more uniform. And the difference between the two is about every 4 molecules or so, you see a long chain branch off of Dow's stuff, which is based on a constraint geometry catalyst. And that long branch allows the material to process better. So you have the same physical properties, but you get better processability. And here's one of my favorites. This is one where you're really getting into control, and I'm not going to go into how you do this, but you can actually now make blocks. So you have a hard block and then a soft block, and then when you basically crystallize this together, you change the temperature profile of how your polymer processes. But you're talking now, notice the degree of control has gone up dramatically with the improved complexity of the chemistry. So it took us a little while to figure out what we had, and this is the simplest way to explain it. Because we had a single site, we got to define kinetics. And now I'm a chemical engineer. We get to play in the game a lot more, because if you can define the kinetics, you can define reactors and design new kinds of reactors. You can understand the conditions to make a given polymer, and you can statistically determine what the structure was. None of this was possible before. The other thing is, for the material scientists, you get to make narrow composition distributions. In other words, much more uniform polymers. They actually follow the rules in all the textbooks. And so you could begin to model things, and the material scientists enjoyed it. Now, the customers in the lighter green, they got to benefit from the improved physical properties. When we talk about activity and incorporation, what this does, because these sites are wider activity zones, you could incorporate new kinds of materials, and you could incorporate more of the same materials like octene than you could before. So what that gave you was whole new product families. And this, as I alluded to, the long chain branching, which then gave the customers a benefit of being able to use new polymers and new applications. So that's all we got. And now when you have that, and I kept saying the word model, you're allowed to now model successfully. We could move to something called molecular architecture. Now I'll make a side note, this is Dow's version. I know a lot about Exxon, but I'm not going to presume to and analyze how they thought about it. I would just say it's very similar. And then I put together a slide we used for years to try to explain to my management what we had, because it's like an elephant and blind people around it. Depending on what you touched, you got a different thing. We had new chemistry. And that chemistry is just the enabler of all this. And that chemistry in the blue, we finally had a way to write the kinetics, the rate equations, for the first time ever. And with rate equations in mass and energy, you could do reactor design, and you could pick the conditions to make a given polymer, and you could do plant design and scale up. First time ever, when we made a material in 100 pounds an hour or 100,000 pounds an hour, it is the same material. And that is just awesome. So the engineers and the manufacturing people are able to really begin to get a lot of control. The other thing is we now made these very simple polymers, and we could pick the polymer we wanted to make. So we could go to the material scientist with the right molecular structures. They could begin to actually put together real structure property relationships and model them and have them work every time, because everything was simple. And once you had that, you could also add in the rheology control, because you had the structure. You could begin to design a polymer. You could look at the post-reactor conditions if you wanted to modify it some more. And then you basically had to understand how you're going to fabricate it, whether you make a film or a milk bottle or a piece of artificial turf. Each of those processes are different. And what you're really measuring against, what does the customer want in terms of performance requirements? Because the customer, you really want them to be talking in terms of modulus and impact and feel versus reactor, this reactor in Louisiana running this catalyst, and I want this product. So you bring in your customers, and if you now notice, we've involved all of the functions. We have marketing, we have sales, we have development. They're all kind of on the outer rim. You have a way to integrate working your team together. And we actually built in Dow, anyhow, we call this 6 days, and I'm not going to go into why, but 6 days. And we actually built it the way I described. The way we operate, it's the other way around. With some fancy math, you can start out with what does the customer want, therefore what structure do I build, and what conditions do I have the reactor run, and what costs do I have. And if that doesn't work and the market's big enough, you can go up to that upper right-hand side and do molecular modeling to say, well, what structure should work, which is how we got that blocky polymer. That blocky polymer lets you run at much higher temperature for operating conditions. So you integrate all of this, and now you have a computer program. And you say, so what? Well, a typical product development life cycle on the process before would take 6 months to 2 years, and with about a 35% hit rate. This is 6 days, or actually it takes about 6 minutes to really run the program. It takes longer to run the pilot plant. But call it typical time length's about 2 months, the hit rate's about 85%. And typically when we don't hit it, it's because the customer didn't ask for the right thing. It does exactly what they ask for. Sometimes they ask for the right thing, sometimes not. And people say, that's crazy, but I guarantee you, our customers know all about this. And that whole thought process, you sit there and say, you can do it on ethylene? Well, why can't you do it on propylene or styrene or epoxies? And so this, once you solve it for this, like anything else, as an engineer, you go try it on everything else. So the products that came out, a huge number of products. These are Exxon's and Dow's. There are other people's out there, but they're basically under license. And we started launching products in '91, latest is 2008. I think there's 17 on there. It's about one a year. And some of them will look very similar to each other if you're Exxon or Dow, but we've got a huge range of products. which is what drove that 13 billion pounds. So what was the impact to the industry? First, our market is slightly different than an educational institution. We want to make a lot of money because our bosses spent a lot of money on this, trust me. The modeling approach can be used on other polymer systems, and particularly in Dow, we're off doing that. We alluded to, there was actually two things we developed, at least in Dow. One was this: we had to rethink how we do development, because instead of spending 2 years we're now spending 2 weeks to do development, we totally had to rethink how to do development. We called it speed-based development. Had nothing to do with the drug. It was how fast we could go. Our production plants grew from 500 million to 1 billion pound trains. Just to give you an idea, when we go build a train, you got to buy half an ethylene plant. That's about $300 million. You build your polyethylene plant, that's another 300 million. Throw in another 150 million for infrastructure. One train, 700 million. So if you can go from 500 million to 1 billion for about the same capital, trust me, that's a really good deal. And we used combinatorial chemistry and any other thing we could get our hands on, because now all of a sudden we had a system where we could attach it, because we had all these models. And so we used Cimex technology. Actually, both Exxon and Dow did it, and we bought that capability. So we went and borrowed the stuff developed for the drug guys to get the new catalyst systems and to do our material science. Our customers are not you, really. Our customers are converters, people who make the stuff. The impact to them is they could switch from talking about products out of a reactor to talking about what do they really need the product to do, which then cuts cycle time and improves their accuracy of their product design. They did have availability of all kinds of new materials to do new applications. They got a quicker and more accurate design time. We could tell them in a week if we couldn't do it. Pretty simple. I mean, if we can't do it, then it saves that 6 months to 2 years. They can work on something more productive. The other thing is the way the processes worked out, we had much more consistent and more high quality product, which then allows them to do much better processing. If they aren't having to tweak all their machines all the time, it makes them more money. Finally, to you, the consumer, you had lower cost systems. Sometimes you might notice that, sometimes you might not. Depends on what the processor wants to charge. You have a lot less plastic because we down-gauged. Some of your garbage bags, if you ever notice the thickness of that over the years, they keep getting thinner and thinner and thinner. You had much more recycle opportunity. This stuff's easier to recycle than some of the other polymers it replaced. And then actually the part that I had the most fun with, to be honest, and one of the neat things about this business, you can actually come around and bring out your favorite product sample without having it do bad things. And in this whole industry, most of you know what a prepared salad bag is. You should. And what this is a whole new industry, and what it is, it depends on the air migration through this material, and that's an affinity or an exact, and you have to use kind of a metallocene material to do that. My wife's favorite, and I promised I'd bring this back, this is a Crocs shoe. And what's really neat about this, besides they're really comfortable, is it's cheaper to make it here than ship it from China, because we injection mold this. There's almost no labor cost. But the design, and then it went through a crazy phase there for a while, so we were hustling trying to figure out how to supply. But this is a fantastic technology. Actually, it's a refrigerator gasket design that one of our guys moved over into that market. Okay, this is stadium grass, and I laughed at the guys when they came in and said, I want to work on stadium grass. I said, what kind of market's that? And they said, you don't understand. And they were right. It's absolutely a huge market. And what we have is stadium grass before, it was durable, but when you slid on it, you abraded. Look at this audience, you probably haven't slid around on a soccer field very much in recent times, but this is very soft. So you can slide on it, and that whole market's just taken off. And the first set of performance requirements we got was the following. We would like it to feel like bluegrass in May after a light rain, 72 degrees Fahrenheit. I said, well, what did you do? We worked on it a little bit, but this, and the neat stuff about this, and I got this from Controlled Products, they've even built dead grass in the bottom here to make it look aesthetic. Now, a car bumper. My bag is only this big. So I think you can all visualize car bumpers. It was one of our first applications, and what you want is better impact properties. So when you run into something, you don't have to go out and get it replaced, you just sort of buff it off. And new adhesives, what this is, you seal the cardboard. And we developed some materials that the pot is much cooler, so you don't burn people. It doesn't degrade, the glue doesn't degrade, so you don't have to replace the pot. And more to the point, you get about 30% more spread, so you use less material. And last, but not for sure the least, is my favorite, is a wine cork. It has no odor. And somebody had to travel through the Alba district of Italy, testing this out with the Italian winemakers because they're the most innovative. And they're testing the cork, and we're testing wine. It's a true story. All right. So there's a huge number of products that were allowed because of this. So in summary, we changed again, and we've created a huge amount of value. And the chemistry and engineerings and way to development, we changed everything. The concepts we're using for the rest of the plastics industry, and innovation and value can happen to even the simplest systems if you have the right kinds of people. And I think in Texas, we have the right kinds of people. And I really appreciated Mr. Tillison's comments that we need to keep the right kinds of people. Because it's really all about people. And this is kind of 2 seconds on speed-based. It's picking the right kind of people. The people know how to do innovation, putting them with and they make connections, new connections. That's all what it's about. That's what you do in your business. So you have to have the right leadership to make sure the environment's right to make that happen. And you need a commitment to slug it out, because sometimes these are not 6-month projects. This was a 15-year development to get the model that we can then do it in 6 months. But I will say that we had products on the market in about 12 months after we decided to do it, so we moved right along. And then finally, you have to have execution. And I think this was probably the biggest lesson we learned, is how you can do that, and it works on anything. We tried it on all kinds of systems in Dow, and in fact, in a little adventure we're doing, which is something related to carbon, we're using the same approach with the same amount of speed. So I want to thank you for your attention. It's been delightful. I can't wait to see the next parts of my body coming up that I might need some help on. Thank you.